All right, so phonetics is often divided into three areas. There's articulatory phonetics, acoustic phonetics, and auditory or perceptual phonetics. Now, we've covered the first two in some depth. This week and next week, we're going to cover the third. This week, it's the physiology of hearing, and next week, we apply that to speech perception. As usual, this video is going to review some stuff that happened last week, preview this week's material, and then note the important stuff coming up. Last week, we walked away from the acoustics marathon and had a look at suprasegmentals. The lab was submitted, and I'm aiming to finish marking early this week. I'm sorry for the wait. And that's it for last week. Okay, so if you remember in week 4 when we covered the vocal tract, this week is heavy on the anatomy and physiology. And just in case you're not familiar, I want to point out the distinction between those two terms. It can sometimes be quite useful. Anatomy refers to the physical structures, where they're found, what they're made of, how they're connected to other structures. Physiology refers to how they operate. The title of this chapter in the textbook also refers to psychophysics. So if we use the parts of that word, we can summarize it as the way that physical things, physics, the way that physical things such as acoustic signals are transformed into psychological things. That's the psycho part of psychophysics. Psychological things such as the perceptions of sound. The textbook starts with a tour through the anatomy and physiology of hearing, starting at the outer ear and moving inward. Now, the outer ear consists of the auricle, which is the visible part of the ear, and then the ear canal, and then the eardrum. You'll notice here, and as we go on, that there are common names and fancy names given for a lot of the structures we look at. If it were entirely up to me, phonetic science would ditch the fancy names and just use the easier ones. Of course, it's not up to me, so it is worth you learning all of the different terms. Learn auricle, but feel free to call it ear. Learn meatus, or however you pronounce that, but call it the ear canal, and so on. What is up to me is how I test you. And in my testing, you're perfectly free to use either form. But do keep this in mind. Whether you call it the tympanic membrane or the eardrum, you're still communicating in a scientific venue. They're both technical terms, and I expect them to be used with care and precision, right? Eardrum should be used just as precisely as tympanic membrane. Anyway, the ear canal. So we get an interesting look here, a callback to that bit on tube acoustics that we learned and damping. In how sound is transmitted through the ear canal and what different frequencies or how different frequencies are affected. And then we move on. Because all the outer ear really does is transmit sound to the middle ear, or the tympanic cavity. So the main characters here are the ossicles, those three tiny bones. And I always remember them as hammer, anvil, and stirrup. I grew up on a farm, so I actually did encounter those objects that they're named after. So those are the names that stick with me. As I did mention just a moment ago, it is probably worth knowing the Latin versions, right? So that's what... right. The malleus, the incus, and the stapes. Because you will come across them, but you don't have to use them in this class. The main point of these bones, which isn't immediately apparent from any diagram I've ever seen, but it's explained nicely in the textbook, is the amplification of the signal from the eardrum to the oval window, which is at the other end of the middle ear. We also learn how the body can attenuate sounds, make them quieter, by engaging some of the muscles in the middle ear to dampen or interfere with the movement of those ossicles. And just an interesting side note, the stapedius is the smallest skeletal muscle in the body, and it is one of those muscles. It's attached to the stapes. That's the fancy term for the stirrup, which is the smallest of the ossicles. Right, and it's important not to forget the Eustachian tube, whose role in hearing is similar to the role of that little hole in a microphone compartment that we read very briefly back in chapter 7. And that role is we need to be able to adapt to changes in the ambient sound pressure, like weather and whatnot, or else the eardrum would spend most of its time puffed out or puffed in and too tense to transmit the sound. Okay, so the sound has hit the outer ear, it's been transmitted to the middle ear, the ossicles have amplified the movements across to the oval window. So now we dive into the internal ear, as it's called in the textbook, or simply the inner ear. And the inner ear actually encompasses more than what we're interested in phonetics. In hearing, the part of the inner ear that we care about is the cochlea, or cochlea. And you might know this term from hearing about cochlear implants, which are one form of hearing aid. So this tiny coiled structure is where the real magic happens. It's where pressure waves finally get converted into neural impulses. And it's also where things get complicated, both conceptually and terminologically. The textbook actually here kind of stops giving alternative terms for most of the structures, but I am going to give some alternative terms here, some slightly simpler terms. At least for me, it helps to have a more English-sounding vocabulary to deal with. Right, now, remember the outer ear and the middle ear, they're filled with air, but the inner ear is actually filled with lymphatic fluid, with a fluid. So anyway, the sound comes in through the oval window, and in figure 1.3 in the, or figure, sorry, 11.3, 12.3, figure 12.3 in the textbook, we find the oval window on top of the basilar membrane. So I'm going to use above and below a little bit here, but remember that the whole thing is in fact coiled up. A little dizzying, but we'll use this diagram to kind of simplify things. Anyway, the sound comes in above the basilar membrane into the scala vestibuli, and this space can also be called the vestibular duct, right? You think of air ducts or something, passage. So the sound travels along this duct, hits the end, the helicotrema, and then rounds the corner and travels back through the scala tympani, or the tympanic duct, to the round window, which is below the basilar membrane, and also looks out onto the middle ear. Now, along the side of the basilar membrane, which is between these two ducts, is the scala media, and the simpler name for that is cochlear duct. So once we've got this general layout of the cochlea, the textbook takes us through resonance theory, which was an early plausible idea about how pressure waves in these ducts, the vestibular, tympanic, and cochlear duct, get converted into frequency-coded nerve signals. It's good to read through this, get a sense of why it might have seemed plausible at the time, but ultimately what I'll be testing you on is the currently accepted traveling wave theory, which the textbook quickly moves on to. And we're told how the particular shape of the cochlea, the fact that it narrows, but also it narrows sort of above and below the basilar membrane, but it also widens parallel with that membrane. How this affects which waves have the greatest strength at what points along there. And I'm not going to try to reteach the material in this video. The video is meant to kind of prepare you and frame the material for you, and then you can learn it from the textbook and any other resources that you have access to. So I'm not going to go into detail, but you should be able to recognize the structure of the organ of Corti in that cochlear duct, with its tectorial membrane, inner hair cells, outer hair cells, and the stereocilia. Get a sense of how they all work together to convert those sound waves into nerve signals. I find the textbook's description quite good, but I know different people have different levels of success with any particular presentation of something. This is quite complicated. I'm linking the Wikipedia article on the cochlea in the description of this video, just in case you find that a little bit helpful. It has some of these alternative names for the structures, some of the ones that aren't given in the textbook. And it presents things a little differently. I think it's still a good presentation. Right. You also need to make sure you understand the concept of tonotopic encoding. This is the idea that different frequencies are mapped to different spots along the cochlea, from the Greek tono, meaning frequency, and topos, meaning place. Right. The physiological part of the chapter ends now with a discussion of autoacoustic emissions. These are sounds emerging from the round window as a result of how the outer hair cells respond to the incoming sound. And these emissions are actually used in hearing tests of newborn infants and in some other contexts where hearing loss, suspected or potential or whatever, may be due to the function of the outer hair cells diminishing. Okay, so now we've spent a bunch of time looking at the elaborate way that our bodies convert acoustic signals into nerve impulses. Now we look at the psychophysical consequences of that. That is, how our perception of sounds relates to the acoustic properties of those sounds. And here's how where I need to wave my hands, and I want to encourage you to pay really close attention to a new distinction. The measurements that we looked at in recent weeks, hertz, pascals, decibels, seconds, these are all physical scales, acoustic scales. They're properties that you can measure directly from the physical waves, right, or from a digital representation of them. They represent the properties of the sound as it exists out here. But we're about to start looking at scales that don't represent the sound out here. They represent the neural and perceptual effects of that sound in the brain and in the mind. The perceptual scales are not the same as physical scales because they're measuring an entirely different kind of thing. And this is going to be important to remember because it's going to be easy to forget because of the particular terms that we use. So let's start with frequency. We revisit the idea of logarithmic scales. The octave and semitone system, used to describe musical notes, for example, is a logarithmic representation of frequency, just like decibels are a logarithmic representation of amplitude. And if you look at the formula for them, it looks very similar. Some of the constants and stuff are adjusted. So by contrast, the hertz measure is a linear representation of frequency. So you have linear and logarithmic. Now, hertz and octaves and semitones are all physical measures of frequency. But what we're after here is a perceptual measure. And the perceptual correlate of frequency is pitch, right? And it's really easy to use pitch to refer to frequency. But when we're talking about speech perception, it's important that we keep these terms separate. So beware. All right. So for pitch scales, as opposed to frequency scales, we have the MEL scale, the BARC scale, and the ERB scale, standing for equivalent rectangular bandwidth. And those latter two are actually multi-dimensional scales because they incorporate not just pitch, but this concept of critical bands. So read through the textbook, see how these scales are constructed and what it is that they're representing. After frequency, we go on to amplitude. And amplitude, the physical measure, has the perceptual correlate of loudness. So loudness is what you hear. Amplitude is what you can measure through microphones and physical equipment. And there are two main ideas to assimilate when we're talking about loudness. One is that your ears aren't equally sensitive to amplitude at all frequencies. We're more sensitive at some frequencies, less sensitive at other frequencies. And that wild graph in figure 12.6 with all the sort of curve, it's got the grid and then it's got these really elaborate curves in kind of almost parallel layered. That's an attempt to capture this fact, the fact that it takes a greater amplitude at very high and very low frequencies to produce a sound that we perceive equally loud to a sound at some mid-range frequency. And the Fawn scale is designed to account for this fact, so the Fawn perceptual scale of loudness. And the other main idea with loudness is that although decibels are a great convenience, they don't completely reflect our perceptions of relative loudness. So the Sohn scale, which is kind of an enrichment of the Fawn scale, the Sohn scale covers that adjustment as well. And then finally in the textbook we get a brief note on duration, which is a physical dimension, and length, which is a perceptual linguistic distinction. Now, perceptually, we don't get a new scale to map to duration. Duration, the physical measure in seconds. We don't get a perceptual scale to correspond to that. We just get a reminder that languages use duration in different ways, from variations of speaking rate, which is a paralinguistic phenomenon. It doesn't encode specific linguistic contrast, but it does carry some other kinds of language-adjacent information. To suprasegmental length contrast, short versus long consonants, short versus long vowels, which is a categorical distinction of, in most languages that use it, it's a two-level categorical distinction. Okay. So that's it for our whirlwind tour of this week's material. Go through the textbook, go through the links that I give it. Excuse me. Go through the links I give in the description. Excuse me. To really assimilate this material as fully as possible. The 5th graded quiz is on Wednesday, March 31st. That's the day after I'm posting this video. And it covers the last acoustics chapter, the acoustic characteristics of speech sounds, and the suprasegmentals material. So make sure you've had a go at the practice quizzes for those modules before jumping into this quiz. Next week is when the 3rd phonetic transcription is due, and you should find the audio for that assignment up on eClass now. It's difficult because this 3rd one isn't English at all, not Canadian English, not any other variety of English. But for all our sakes, I've used a much shorter sample of speech, so I hope that helps out a little bit. Anyway, enjoy that, and I look forward to seeing you hopefully at the tutorial.